All right. All right, well, actually, we don't need to get too stressed. I like this section that we're on right now. This is section 4.7, Applied Optimization Problems, which sounds fairly awful until you realize that it's just combining two of our favorite things. That whole business of using derivatives to find maxima and minima, which I think, in the great scheme of things, we kind of liked. Compared to a lot of things we've done in this class, like limits and stuff like that. I think that business of finding maxima and minima certainly seems like it was something you guys liked a comparatively large amount. And it combines it with the kind of problems that we did. Remember back in, was it Finite or whatever last semester that had the optimization problems that we did those different techniques with and so on to figure out like the ideal number of records to make and all that kind of stuff? Yeah, it's basically combining those two ideas, but we're not going all the way back to, oh my gosh, what were those? Simplex tableau, or whatever those techniques were. We're not going all the way back to that. Rather, we're just going to be using kind of the same sort of strategies with calculus. Here's one of the problems they give us. I think this is the first example in this chapter. It's saying, in the story problem, suppose there's like a wall in the garden. This is like a brick wall out there someplace. We're looking at it from above. And it's saying you want to make a fence around the biggest area you can make in the garden. Okay? And you've got 100 feet of fence to work with. What's the biggest area you can put in your garden with 100 feet of fence if you are using the wall that's already existing for one side? So you've got 100 feet of fence and you need to make 3 sides like that. Okay? And just to keep it relatively simple, let's say we're going to work with rectangles. Okay? I'm not sure if the answer would be all different if like you could make circular areas with your fence or whatever.
So only 3 sides.
Yeah, you only have to worry about 3 sides, right? The brick wall will make another one. So like if this side has length x and this side has length y, that makes this side also length x, and apparently 2x plus y is going to have to equal 100. And it's saying what's the biggest area that you could make a fence around with this set of restraints. Alright, so in other words, A, the area of this garden, is what you're trying to optimize. We need to find the value that would produce the most. Now, your book makes this harder than it needs to be, but for good reason. But let's keep it simple first. Alright, A equals x times y. That's not so big of a deal. But there are restraints on how long x and y can be. I mean, y plus 2x has to be 100. I guess strictly speaking, it has to be less than or equal to 100, but I think we can agree that we need to use up all the fencing to get the biggest area possible, so we don't have to go down that road, right? It's going to be equal to 100. What the book suggests as a problem strategy is get everything except, in this case, the y on one side, and then substitute that in. So like y equals 100 minus 2x. And then plug that in here for y. So x times 100 minus 2x is the area, just depending on then on one side. And we can actually multiply this out. This is going to be 100x minus 2x squared. So the area of the garden that we make using that wall is 100x minus 2x squared. We want this garden area to be the biggest it can possibly be, so we're looking for a maximum then of this equation. We're trying to find the value of x such that 100x minus 2x squared is a maximum. How do we find the maximum of an equation?
Set it equal to 0 after you find the derivative.
Take the derivative.
Set it equal to 0.
So let's take the derivative of this. That's going to be 100 minus 4x, right? I probably should check to make sure I haven't made a silly mistake on this problem here, but I'm pretty sure I'm okay so far. Alright. And then we set that equal to 0. So that we find the max, well, we find a critical point anyway. 0 equals 100 minus 4x. So can we agree that x equals 25? Now what the book actually does here is it first makes a sketch of this equation where it's area with respect to x, and your function looks something like this. Okay? And you have your maximum at x equals 25. So if x equals 25 and 2x plus y equals 100, apparently y is equal to 50 when you make the biggest garden possible, which will be 25 times 50. Honestly, other than the trick of realizing what we've got to do then is come up with an equation and get rid of one of the variables by saying, you know, hey, let's put everything except the y on one side and then substitute that back in. Other than that trick, this was not that big of a deal. Your book makes a slightly bigger deal of this. For example, it said, what if the answer had been negative? What if, here I'll try what if your answer had been x equals negative 25? Then what? Well, that would have meant, like, the graph of this equation looks something like this. Oh, I don't know. Let's just say something like that. Where its maximum is at negative 25. Is negative 25 a good length for the wall? So if x is negative 25 and 2x plus y equals 100, let's see, so y is 150. So we're going to have our wall go like 25 meters this way, 150 meters this way, and negative 25 that way. I mean, it clearly doesn't work, right?
Right.
There's constraints. There's other constraints in here, like x has to be greater than or equal to 0, and y has to be greater than or equal to 0. Let's say the equation had worked out, though, that this is where the maximum was. And that is where the maximum is. It just so happens the math works out that it's at x equals negative 25. Well, then what? Well, that's not a viable option. On this equation, we have to have at least x is greater than 0. And, well, you know, the sum of the two has to be no more than 100, so x has to be less than 100, right? We can't have one side of the fence be more than 100 feet because we'd run out. In fact, x can't even be more than 50. We wouldn't have enough fence, right? So it could be that our solution is one of these places inside here. It might not be a relative maximum, but it's a maximum on a range. So your book gets a little... See, they kind of like started throwing all this at you. The actual business of finding it when the local maximum was in the range we cared about and was physically possible and so on, that's nice. But often that won't be the case. The maximum, we got one of those kind of problems where they can bake cookies and pies and they get so much money for each cookie and so much money for each pie and they got to figure out what's the best way to make money, how many cookies, how many pies. Okay, the actual maximum might be making 37 pies and negative 200 cookies. Can't make negative 200 cookies, right? On your range of, best you can do is 0 cookies. You know, your range, it might be that you're only talking about the relative maxima in that range. That's not going to happen all that much on the particular problems in this chapter, just because this chapter is about calculus. And so it wants you to be using things like the derivative to figure this stuff out. Okay, but I mean, like on page 441, they have a whole table there called problem-solving strategies for solving these optimization problems. And they're basically the strategy we just walked through. But let's do like example 433 together. Maximizing the volume of a box. An open-topped box is going to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. Let's make ourselves a picture here. I didn't do this one in advance, so I'm excited to see how it works out. Alright, so we start off with a 24 by 36 inch piece of cardboard. Yep. And we're going to remove squares from the side. Alright, so here's our box, our piece of cardboard. It's 24 by 36. This is not a box. If you put something into this box, you will be disappointed. It will go out the sides. But we could cut corners out and fold the thing up. And then it would have a volume. It would hold something. And I believe the problem is saying what square size would be cut on each corner to get the box with the maximum volume. So we need to know the volume of this box. And then we're going to figure out, well, okay, can we agree that all of the corners are going to have to be cut the same way? Right? Clearly cutting some of them bigger and some of them smaller will not make a happy box. Right? Alright, so let me just, so I'm using the same symbol they're using. What are they calling? They're going to call it X. X is the length we're cutting off right here. Alright, what is the volume of this box? The volume is going to be length times width times height. Length, 24 minus 2x. 24 minus 2x is the length of the box in this direction. It'll be 24 units wide minus this x, times the width, which is 36 minus 2x, times the depth of the box, which is just x. That is our volume of the equation here. Alright, did the book actually expand that into like just an ordinary polynomial? I don't feel like doing all that, asking for trouble there. Yeah, okay, so that is 4x cubed minus 120x squared. 4x cubed minus 120x squared. There's one more term. 864x. 864x. Before we get too far on this problem, let's think about what a graph of this equation is going to look like. I mean, if I had a graph that was x versus the volume of the box, what is the volume going to be of the box if x is 0? If we didn't cut anything?
0.
Yeah. If I cut this down here at x equals 0, the volume of the box is 0. And if I grab, are we in agreement that I could cut at some point far enough in that like I'd lose the whole sides of the box again and it would be 0 again? There's some way out here someplace where I cut the box again and I have no volume. I've cut the corners too big. So, but places in between, there is some volume to the box. Can we agree, and the function has like x squareds and stuff like that in there, it probably looks something like this, right? There's, at no corner cutting, there's no volume. At some corner cutting, there's no volume again. But in between, there's some place where the maximum is. All right? How are we going to find that volume? Well, we're going to need the derivative. The derivative of volume with respect to x is going to be 12x squared minus 240x plus 864. And what we're going to do is we're going to find the places where that slope is equal to 0 to find the critical points. Oh no. It's got a squared in it. However, are we going to find the values of x that make this true?
Oh, we could, what's that? X method.
Oh, yeah, I don't even remember what that thing's called.
Or we could do, what's that?
Quadratic equation?
Yeah, b plus minus.
Yeah. Who remembers the quadratic equation off the top of their head?
Oh, I think I can guess it.
Go for it. Guess it.
All right.
This is the A, this is the B, and this is the C.
B
Yeah.
plus or minus the square root of AC minus B, or B minus.
You scared it out of me. Now I can't remember it either. Oh, good. Minus b plus or minus the square root. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay.
I was gonna guess.
I know it. She just Googled it that fast. It's one of those things that I know until that suddenly when people start shouting A's and B's, I get all turned around. All right, we could do that. And we would get two values of the b. I'm sorry, of x. For what it's worth, the book says that they are 10 plus or minus the square root, I'm sorry, 2 times the square root is 7, is that right? I don't feel like doing all that math. Okay. I like this problem because notice we've got two solutions here. Let's think about what they each are. What is 10 plus 2 times the square root of 7?
The answer is approximately 15.292.
What is 10 minus 2 times the square root of 7?
The answer is approximately 4.708.
Got two answers there. Man, I was hoping one of them would be negative. Because then we would have, we can probably get a hell of a big box if we could make a negative cut and like be adding on to the size of the box. But one of these is a good guy and one of these is a bad guy. 4.7. So like on this side that is 24 inches over here, we go out 4.7, 4.7, 4.7, 4.7, something like this. And we've got a little chunk taken off the side. I'm happy about that. 5.3. Sorry, 15.3. Notice that the middle here is 12. So if you're cutting over 15 inches this way, and then you could do that, but then you cut 15 inches this way, and you're going to be sad. Right? One of them doesn't have a physical meaning. Right? I don't know the final answer here as to what, that means that they would, there's no physical meaning to that. Okay, the box doesn't have it. So the correct answer would then be to cut 4.7 inches off from each side, and you'll get a box with a maximum volume, and the book probably annoyingly makes you actually solve that. Which, whatever.
I'd never solve that.
What?
I'd never do it.
Why not?
It just wouldn't.
What if the book told you to? What if I did it on a test?
I don't have to listen to the book.
You're your own man. How would you solve it? You put this in for x, right? 24 minus 2 times this number times 36 minus 2 times this number times this number, and you'd be done. Sounds no fun. We won't do that right this moment. None of these problems then are terrible. They just occasionally have weird situations like that where you have to make sure, hey, wait a minute, which of these is the right answer? But overall, I think as these kind of problems go, this is relatively straightforward. In fact, I feel good about the fact that there aren't really even all of that many problems on this homework set. Because I feel like you're going to be able to do it just fine. I'll be honest, I have not done all of the problems in this homework set. I'll be even more honest. I usually haven't done all of the problems on the homework set, so I'm not entirely sure. But in this particular case, I'm a little worried that maybe one or two of these will turn out to be harder than we think. But we can do them together as a group or whatever and figure it out. But for today, your problem set comes from page 451 and forward. And it is numbers 315 through 331 odd. 315 to 331 odd. So what, it's only like 15 problems. And I think it'll be okay. All right, so we'll go ahead and stop the camera, and I'll get the pen back over to Mrs. Russellberg. And